Yeah, we'll go ahead and get started. So I hope everyone had a good fall break. And today we're going to have a lecture on reinforcement learning. So this is an area which is rapidly gaining more and more prominence in NLP and advanced NLP. So this semester we're going to have a slightly larger focus on it than last semester. The way things are structured is in today's lecture, we will go through the kind of basics and background of reinforcement learning. And it really doesn't have anything to do almost with NLP. But the ideas are really important to at least see once, at least see the foundational ideas. And then in the next lecture, we'll look at some applications of these ideas to NLP and to large language models. Then in the third lecture, it's kind of related this semester. We'll take a look at agents. And a lot of these tools or even ways of looking at problems that we get from reinforcement learning will be very useful for thinking about those kinds of problems and even training models to kind of function as agents. So with that, we can get started with today's lecture. So first, I do want to just motivate this and contextualize it using language models and using things we've talked about. So really the primary learning algorithm that we've used has been based on what's called supervised fine-tuning. So here we start with some base model. Of course, that was pre-trained with some pre-training algorithm. And then here we have this task data, such as instructions and inputs and outputs. And then we fine-tune the model, and you can get a model here, like an instruction following model. And the algorithm that we used to do this was maximum likelihood. So in a bit more detail, we had this data set of inputs X and outputs Y. And really the objective or the goal was to maximize the likelihood of predicting the next word in the output given the previous words. Okay, so today we're going to be looking at different loss functions or different objectives, which is why I'm putting this equation up here again. So we'll see different versions of this today, and we'll kind of compare and contrast them. But first, we can just intuitively think about what this is trying to do. And when you think about it, it's really just using this data set that is provided and in some sense learning to imitate it, right? Like we're specifically increasing the probability of outputs that are provided in the data set, and we're only focused on these outputs that have been provided to us. Okay, and then in doing so, the hope is that you're not just memorizing this data set, you actually get some useful generalization. So for instance, you can give the model a new instruction, and it might actually have enough generalization to give you a kind of good output. Okay, and so this can be very powerful. But what are some limitations to doing this? Okay, well, first one, I'll call it task mismatch. So typically we want to use a model to actually perform specific tasks. So for instance, we might have a dialogue system and we want it to have kind of helpful responses or ones that are non-offensive. Or we might want to say solve a problem and you really want the model to produce some correct solution. Or maybe you want the model to generate some code and you want it to be correct code. So you might like run some test cases. Okay, and when you think about it, what we're saying is that we're kind of assuming that a probable response is the same thing as a response or output that satisfies our task criterion. Okay, so it's kind of saying, well, maybe if we make a lot of good solutions more probable, then we'll get a correct solution, things like that. Or we'll get code that passes test cases. Um, and the issue is that this isn't always the case. And a second question is like, if our goal is to perform a task, why don't we just directly optimize for that task criterion? So what if we could like specifically train a model and set its parameters so that it maximizes this kind of reward, which is like a correct solution or a helpful response? Second is this supervised fine-tuning is based on data, and sometimes there's a mismatch in the data. So what do I mean by that? Well, let's say that we train a model on like responses from Reddit. Well, then maybe some of those are offensive, and then when we go to use it in our task criterion is to have non-offensive responses. Or let's say that we train it on some code, like from GitHub repositories or something like that, and there's some bugs in the code. Um, and a second issue is that sometimes we don't really have data specific to a task or specific to some functionality that we want out of the model. Okay, so a good example of this is these chains of thought. So if you take, say, like a kind of difficult math problem, then maybe on the internet, if it's a popular problem, you could find like one human written solution for it. But you could imagine that like maybe the model wants to solve it in some different way, and we just don't have a large amount of examples of this functionality. We in some sense have to kind of like try generating data with the model. And then similarly, let's say that you have some different prompts for like your chatbot, then maybe you don't have helpful examples of helpful responses for all different prompts. Like maybe you have some detailed, I don't know, critique of some essay in some like specific area. Then kind of getting a lot of data to be able to just supervise fine-tune the model so that it's good at responding to that prompt might start to be difficult. And then the third, and this is somewhat like a technical issue, maybe, you could call it exposure bias. So this is just saying that if you look at the supervised fine-tuning, then in some sense it's telling the model to imitate the examples that we've shown it. But what it doesn't do is it doesn't really train the model on mistakes or on bad examples. So for instance, let's say that we train our model and it solves a problem and then it makes a mistake. Well, then it's actually never been trained on data that actually shows a mistake. And then you could say like, okay, maybe we can collect a lot of that data, but then you get into the issue on the previous slide that it gets harder and harder to kind of collect these more specific types of data. Similarly, let's say that we want to train something which like navigates web pages. Well, then maybe we can kind of navigate the page ourselves and show how to perform the task. But that doesn't necessarily show what happens if you like click the wrong thing. And so we want the model to be able to kind of recover from these mistakes. Um, so today we're going to talk about a framework called reinforcement learning. And when we apply it to language models, which will mostly be in the next lecture, it will look something like this. So first we'll generate with the model, and then we can evaluate the model's outputs with some reward function. Okay, and then based on that reward function, like here we have a correct output, here we have an incorrect one. Based on that reward function, we then do some learning, so we update the model parameters. And the cool thing is that as long as you have a good reward function, then you can try to apply this to a variety of tasks. So it's a pretty general framework. So some key differences. Now we can directly optimize for our task criteria, say like correctness or useful responses, as long as we can kind of build a reward function which kind of quantifies the task criteria. Second, the data is now being generated by the model, or at least the outputs. Um, and so this kind of lifts the constraint on needing the kind of human written data. And the reward function even tells you kind of how to use it. Should you use it to uh, kind of increase this type of behavior, or should you penalize this type of output or behavior? And then third, as long as we can evaluate the reward, then the models can basically learn from any output or any trajectory. So in particular here, we have an example of some like offensive output. And if you think about it, it's not clear how to use that with maximum likelihood. Whereas here with reinforcement learning, we can kind of assign a negative, low reward to it. And the reinforcement learning algorithm will actually get some learning signal even out of this kind of wrong or mistake kind of trajectory. Okay, so in today's lecture, we're going to focus on what is reinforcement learning, give you some of the basic ideas and basic tools from reinforcement learning. And we will focus on this class of algorithms, which are called policy gradient methods. Okay, and the reason I'm focusing on these is currently they're the ones that are mostly used with language models. Okay, and I think it's really good to see the kind of details of them and even to see the methods presented separately from language models. And then these will be the next lectures, as I mentioned. Okay, so what is reinforcement learning? Well, coming up with these general definitions is always hard. So I actually got this one from a textbook. And it says it's a branch of machine learning concerned with learning from interaction. Okay, so we have a notion of interaction, and you have a notion of an agent and an environment. Okay, so the agent is interacting with the environment, and broadly speaking, the goal is for the agent to learn what it has to do in order to maximize some reward signal. And then reinforcement learning itself is kind of corresponds or refers to multiple things. So it refers to a problem, like the problem of reinforcement learning. How do you do this learning? It refers to a class of solutions. So we'll see some algorithms today. And then sometimes, you use reinforcement learning to just refer to the field that studies both the problems and the solutions. So you could say like you're a reinforcement learning researcher or something like that, or submit to a reinforcement learning conference. So in a bit more detail, and we'll go into all the technical details of this today. Here, the agent is receiving some observation from the environment. It's receiving some scalar reward. So this will just be a number. And then it's executing some action and kind of doing this in a loop. The environment is receiving the action, and then it's providing this new observation and providing some reward. Okay, so we'll see a few different examples of this. Okay, and again, the agent is trying to maximize reward. So one example is that was studied a lot, especially like when I was doing my PhD in 2016, is these Atari games. So here we have an agent which is playing the game. And your observation would be, let me see, yeah. Your observation would be the screen. And then your actions are to press different buttons. Okay, and then you could imagine like, okay, if you train the agent really well, well, maybe you want to train it to maximize the score at the end of the game. You could see up here, it's like 41-5. And so maybe you could use this as the reward signal. Here's another example. And you could see as the agent lasts longer in the game, it's getting a higher score. So maybe you could try to maximize that reward. Another kind of common place to use reinforcement learning, I'm not really giving specific examples here, are in motor control or robotics. So here, just broadly speaking, your kind of agent would be the robot. Here, the observations could be a variety of things. It could be camera images. It could be the specific angles of the joints in the robot, things like that. The actions could also be a variety of things. For instance, let's say you want to control the specific joints in the robot. And then your rewards can be a variety of things as well, based on the task. You could want the robot to stay balanced. You could want it to like move something to a target location, things like that. So even in this description, I'm kind of saying, this could be a lot of different things. So you can imagine that this is a whole field. Actually, CMU as a whole like institute on robotics. So we're not going to go into much detail on this today. But actually, we will see a simple example of uh, kind of controlling um, something in this class. Okay, and then there's text generation. So here, one way to frame this is your agent is the language model. Your observations are, let's say, like the input and what it has generated so far. And your actions could be generating like the next token in the output. And then your rewards will depend on the application. We'll see a couple examples in the next lecture. Here, let's say that we're solving these math problems, and so our reward is basically, is the final answer correct or not? Okay, so these are some examples, and then now we'll start to go into a bit more of the technical details of how you view these different problems. So there's this formalism, some way of formalizing these different problems called Markov decision processes. And so you can view the setting as being kind of four different parts. So first we have what is called the state space, the set of states. So like in the Atari example, this would be maybe the image of the screen. Then you define some action space. So this is the set of possible actions your agent can take in the environment. So for example, for Atari, maybe you have the different controller buttons. Uh, then you have these transitions. So this is basically modeling or assigning notation to the kind of underlying environment. So here, for instance, when you press a button when you're playing Atari, then the system is going to generate some new state and then show you some new screen. So the transition from some state and some action to a new state is these environment transitions. Then you could imagine that, sometimes you have multiple choices for the next states. So this is going to be a distribution over possible next states. Then here you have the reward function. So you could also view this as being part of the environment. So you could have a kind of probabilistic reward as well. But here we're just saying that, it takes in some state and some action and then gives you this scalar number. Okay, so for example, you could return the game score at each time step. Okay, then the agent is going to take actions using what is called a policy. So this is like the typical name, and the typical kind of symbol used is pi. So here we have this policy pi, and it is taking in some state, and then it gives us a distribution over different actions. Okay, so it might give all of its probability to like some, button press that will win the game, and give like zero probability to something which would cause the, the agent to die. So these are the basic parts of this MDP. And the reason it's called Markov decision process is there's this kind of assumption that the state contains all of the relevant information that you need. So basically, like this state is equivalent to giving like all the previous states, for instance. And that's this kind of Markov assumption. And so it makes it really easy to kind of reason about these things because we just look at, a single state and a transition from one state to the other, things like that. Okay, then one more bit of just formalizing this a bit. So then you could think about like actually having the agent interact with the environment. And you can think of this as being a sequence. So here you get some initial state from the environment. You then take an action using the policy. So here it's like sampling some action from the policy. Then you give the action to the environment, as we saw in the picture before. That gives us some state. We can then get the reward, and then you continue. So now with your new state, you can take a new action, and so on. Okay, and then eventually you'll get to some terminal state. Let's say that in the Atari game, the terminal state is when the game ends. So either you die or you win. Okay, so then a bit more terminology, and you'll see this come up all the time. So you can call this sequence here of like states, actions, and rewards a trajectory. And then you can also call this a kind of episodic setting. So this would be a kind of um, one episode being played out here. Um, okay, and then if we try to formalize the goal a bit more, like the goal of learning or the goal of the agent, we could consider like here you have some distribution of trajectories in the sense that like you can interact with the environment, you can choose actions with your agent. Maybe there's like different starting states, like different game states. And so you can get some distribution of interactions or distribution of trajectories. And the kind of goal will be to find or learn some policy which maximizes the expected reward or expected return over this kind of while it's interacting with the environment. Okay, and so the return here just means the sum uh, of all of the rewards from a given state. So basically, like from your starting state, you want your policy to give you high expected reward. Um, and that's just kind of what's written here. Okay, so let me just go, just to make sure it's clear, let me go through this example uh, in some more detail. So here's another one of these games, Pong. And here we could say that, oops. Here we could say that the state is the like a screenshot of the game, for instance. Then we can give that to some policy. The policy could be, a neural network that takes in images and um, outputs actions. Let's say it takes the action down. Then here you could see that it's moved down a bit. We would actually send that to the environment, and the environment would give us this kind of new observation or new screenshot. Okay, then you could continue this and actually kind of play the game until it ends. And then your reward function could be 0 maybe for all of these kind of intermediate states. And then at the end, you can see whether the agent won or whether it lost and give it a +1 or a -1. Okay, so that's a concrete example of the kind of MDP in this Pong setting. Um, so there's one thing that I want to just clarify, just so that you've seen it before, which is this difference between states and observations. So here, when you think about, let's say like the system that is running Atari, like the actual implementation of the game, then that is in some sense some state which the agent is not able to see, right? Like the agent doesn't actually look at the, state of the code that's being run. Um, Instead, it sees this observation, which is like the screenshot corresponding to the current state of the game. Okay, so there is this distinction between this kind of environment state and an observation. And then you could define the agent's state as whatever information it's using to kind of pick the next action. So Here, if you want, it could be a function of this entire history. Um, right? Like you could implement the agent in a way that it just saves the prior observations. It's not like cheating or anything. But then you could define the state and then kind of use this MDP formalism um, to think about the problem. Um, so you'll see this distinction between states and observations come up. There's actually a different formalism called partially observed MDP, and you might see that pop up in different papers, and that is just helping distinguish between a state and an observation. Let me just go through this example here, and we'll talk about it more next time. So instead of the Atari games, let's look at one way of framing text generation or this like math problem solving as an MDP. So here our state would be a prompt X and the tokens that you've generated so far. So at the beginning, you just have the prompt. Here you have the prompt plus, these. And your actions would be to generate a next token. And here the policy or the agent is just the language model. And you could see that, it's you could use the letter pi if you want. It's this distribution, which is getting the current state and giving you a distribution over actions. Now here is like why it's maybe not the most exciting use of reinforcement learning. The environment is in some sense kind of boring. The environment is saying basically at each step, we're just appending the token, and that will be the new state. And then the reward, let's say that you only are able to evaluate the final answer. Then your reward would basically be 1 if you are at the final step and the answer is correct. And otherwise, for all these intermediate steps, it's just 0. So then if you consider the return, it'll be the sum over all the steps. So it'll include, the reward at the end. Okay, so although I said this is maybe a boring environment, it turns out that this is the one we'll use in next class. Um, and it's the one used in a lot of like state-of-the-art uses of reinforcement learning and language models. Okay, and then just one more thing to know about. So I'll pause it a bit because this will be the end of this section. But today we'll focus on one type of reinforcement learning algorithm. And here I wanted to just give you some broad picture of, the idea that there's other kinds of algorithms. So typically your agent will include at least one of the following. So one way to build the agent is to, learn or build this policy that I was talking about. You could kind of represent this as a neural network and try to learn a really good policy directly. It turns out that you can also, there's algorithms that will try to learn a really good value function. So a value function says for any given state, or you could have one that takes in a state and an action. It says what is the expected return from this state? Or if you take in the action, what is the expected return if I'm in this state and I take this action? And then when you think about it without going into the details, let's say you did this perfectly. Well, then maybe you can actually use this to kind of build a policy. Maybe you can look at each possible next action and say, let's just pick the one that leads to the highest expected reward. And that's a perfectly, valid RL, reinforcement learning algorithm. And then the other thing is you can try to learn this model of the environment. So here I've written it with a lowercase e. So this isn't going to be the actual environment. This is going to be one kind of inside of our agent. And it's going to try to learn, like, given the current state and maybe given an action, what would the future state look like and what reward would I get? Okay, and so without going into the details again, you could imagine that if you did this really well, then you could probably do well at the reinforcement learning problem. For instance, you could simulate like, okay, if I was to take this action, what would the next state look like? What would the next state look like? And what would be my eventual reward? Of course, it's going to be difficult to learn a good value function or learn a good model, but these are like, yeah, kind of approaches to consider. Okay, so in summary, these policy-based methods will try to learn this policy. Value-based methods will try to learn a value function, and model-based methods will involve learning a model as well as some other things. So today we're going to focus on these policy-based methods, and then we're actually going to see this value function come up. It's going to turn out to be useful for kind of stabilizing the training. Okay, but you'll see these terms come up, so it's good to at least have seen these once. Okay, so in summary, the kind of problem setting is we have this MDP or Markov decision process, and our goal is going to be to learn a policy that maximizes the expected reward or return um, in this setting. So any questions about this so far before I go to the next part? Okay, great. So next we're going to go into these policy gradient methods. And these will give us some way of, this is an algorithm for like solving this reinforcement learning problem. And here we're trying to directly learn the policy. Okay, so we could formulate this as some learning objective. Let's say that we want to find the parameters that just, here's like the objective of reinforcement learning. Let's try to directly optimize this. So let's try to find the parameters that maximize this expected return. Um, so in this class, we've talked about using gradient descent. So given some objective or given some loss function, we would take the gradient of the objective with respect to the parameters of the model. And then we can use an algorithm like SGD or Atom or something like that. So the question is like, can you do this for reinforcement learning? Can you just say, here's the reinforcement learning objective. Let's just do kind of gradient descent on the objective. Um, well, it turns out to be a bit tricky. So for instance, let's say that our reward is, whether you win an Atari game or not, then it's not clear how to take the derivative of, winning an Atari game with respect to the parameters of a network. So in general, like sometimes we have these non-differentiable rewards. And then second, I'm not going to go into the details, but it turns out to also be tricky because here we have a full trajectory. And the trajectory involves these transitions through the environment. So at least in the naive case, we would also have to backpropagate through the environment. And again, it's not really clear how to backpropagate, say, through the implementation of Atari. But there's still kind of hope. And so the solution is going to be use a kind of clever trick and get some estimate of this gradient based on kind of interactions or based on sample trajectories. Then once we get a gradient estimate, we'll be able to use just normal backpropagation, normal, SGD, atom, things like that. So the key idea here, and again, this really like underlies, most of the methods that are used today is, I mean, probably the idea is from earlier than this. It was probably invented in statistics. But then the first work putting this into kind of machine learning setting is from 1992, and it's called reinforce. And it uses this kind of simple trick to come up with some estimate of the gradient. So here, let's say you have some distribution P and some function F. So the function on the next slide will turn out to be like the reward, and then here will be a kind of trajectory. But the idea isn't even specific to reinforcement learning. So here we could say like, okay, we want to take the gradient of this this objective here, which is like the expected uh, function value, or it'll be, expected reward. And so this is just writing out the expectation. Then what you could do is you can move the gradient inside of this summation. And then here it's just multiplying by 1. So you have p theta of x over p theta of x. Okay, now here's really the key trick. And if you think back to like intro to calculus, you might remember this. And it's kind of clever here. So it basically just replaces this gradient of p theta over p theta of x with the gradient of the log. Okay, so this is just this identity from calculus. Now, why is this interesting? Well, now we can basically view this as being some expectation um, that that looks like this. And now we have the gradient kind of inside of the expectation. And so what we could do is we can approximate it by just drawing samples. So let's say we draw a single sample, then now you have this gradient approximation shown here. Okay, now you can imagine, and so then this is called reinforce gradient estimator. Okay, and so it looks like this. Here I've just moved this here. You have the function value, and then you have the gradient um, kind of at a sampled output. So you can imagine like maybe this is not the best approximation if you're just drawing one sample. And we'll actually get to that later. But it nevertheless is some approximation. And so now we have some gradient that we can use. So if we apply this to reinforcement learning, then here's what we get in the end. So recall that we want this gradient of the model parameters with respect to the expected reward. Then it turns out that it ends up looking like this. So we have this summation over time steps, and then we have something here which looks like what was on the previous slide. You basically have the return at that time step, and then the gradient of the log probability of the policy of the action given the state. Now I did something kind of subtle here, which is you actually have to be careful to break this trajectory apart into time steps. And it turns out that you can kind of get rid of the environment transitions. And so you can kind of safely write things in this form. The details of this are not like, I mean, they're kind of interesting, but they're kind of tedious. So I made some slides with the details if you're curious after. But basically, the important thing is we get this kind of gradient estimate, which looks like this. Okay, and so again, this capital RT is the return. So at each step, it's like the future rewards. And then this little hat is saying that we've sampled some trajectory with the policy and by interacting with the environment. So then we could think about like what this does. And it's actually, really simple. So let's just look at one time step. Then it's basically saying like, okay, if our return from this state, or if the reward is high, then we're going to push up the probability assigned to the action that was taken at that state. Similarly, if the return is low, let's say it's negative, then we're going to push down the probability of taking the action from that state. So it's actually really kind of intuitive. And you could see that it actually looks kind of similar to maximum likelihood. So here, if we ignore the reward, then we basically have the log probability of the next action. And if you remember when we were talking about language models, the next action is the kind of next token. And so in fact, maximum likelihood is actually a special case of doing this procedure. And it basically says that the reward is 1, and we only sample trajectories from our data set. Okay, so really the core difference with reinforcement learning is that we are sampling these trajectories using these interactions, and then we are incorporating the reward function. So if you followed that, it's kind of cool and kind of interesting, I think. Okay, so then if we put this all together, I've kind of just been showing formulas, but we could put this together into an algorithm, and the algorithm will be as follows. First, we collect trajectories. So we interact with our environment, we call our policy, you play the Atari game, whatever. Then you compute these returns. So at each state, you kind of sum up the rewards. Then you have everything that you need to compute the policy gradient. Now, if you think about PyTorch, it's kind of easier to write down a loss function than to maybe like program in a gradient. So you can also just use this implementation trick, which is if you just set this as your loss function, then when PyTorch, takes the gradient, then it ends up being the policy gradient. And I'll actually show a code example in a bit. And then that's it. So then you use backpropagation and use like Atom or SGD and kind of run this in a loop. And then the reason it's good to walk through the details is, if you followed the argument from before, then this, at least in principle, should maximize the expected reward. So here on the course code webpage, we have this example, and it's based on this environment, which is called cart pole. So here you have this like pole, and you need to keep it balanced. And so your actions will be either left or right. And so here it's just showing the kind of full implementation. So let me just, take a look at the code. Okay, so I think we can probably run it. Okay, so just to make everything concrete, so these environments are implemented using a kind of common interface. So here you're creating the environment, and then here we could take a look at the states and the actions. So it turns out that in this environment, it's not actually receiving a screenshot. You can try solving this task using a screenshot. It's just not here. It's actually just giving it these 4 different numbers. So you get the position of the cart, you get the velocity, you get the angle, and you get the angular velocity. And then if you, here's how I generated that screenshot earlier. Here you can actually take different actions. So your actions will be left or right. And then here it's just showing the environment transitions where the environment's actually changing. Then here's an example of a policy. So it's a neural network, and you're taking in the state. So remember, it was 4 different numbers. And then you just have the simple, network, and it's giving you scores, and you're taking the softmax for each different action. And so you can see here, there's 2 different actions. So for example, before training, it kind of gives us these 2 action probabilities. Okay, and then here's the training loop. And you could go through all the details and use debug statements and stuff if you want later. But it really does follow exactly what I showed you on the slide, these 4 different steps. So here we're basically collecting a trajectory. So you could see we're giving the state to the policy, we're taking an action, then we're getting the next state from the environment and the reward. Then we compute these returns, and I'll get to this discount factor in a bit, but you could see it's kind of summing up the rewards. Then here's the loss that I showed you before. And then it's just doing this normal update here. Okay, so this is the basic policy gradient, and then you can run it. Let's see, should be able to run here, and you can print out the rewards. So it's just training like on my laptop, and I think the maximum is hopefully it varies based on the you know every time you run it, which we'll get to in a bit, but hopefully it eventually solves it. While this is running, any questions? Okay, great. So it actually solved it. So each one of these environments has like a threshold, which means it's solved. Um, so we could take a look at this and you could see yeah, you could see it's kind of crazy. So it was kind of successful at increasing the reward, but you see these kind of wild fluctuations. So we'll actually talk about that in a bit. This is an example of it being kind of unstable. And you see this a lot with the reinforcement learning. Then you can visualize it, and this should be the actual visualization. You can see it's pretty good. So it's taking all these actions shown here. Okay, so that's the really basic policy gradient. And yeah, hopefully I convinced you that at its core, it's fairly simple. But then if you follow all the arguments, it's actually kind of, one way of solving this reinforcement learning problem. Um, so the question is, let's call this policy gradient that I just introduced vanilla policy gradient. And as we saw, it could be kind of unstable. Um, and this environment is pretty simple, right? It's just like balancing this pole. And so maybe this becomes an issue in a more complex environment. Well, indeed, it does turn out to be an issue. And so there's been a lot of research into kind of better versions or better algorithms aside from this basic policy gradient. And you can kind of interpret all the different strategies in, well, there's at least like 2 different types of strategies. One is instead of just using this return here, we can come up with some better way of kind of reweighting the gradient. And then second is maybe we can somehow control the step size. So, maybe this is becoming unstable because it got some really high reward and it like took too large of a step, and then the whole thing blew up. So here's a few common things that you can use for the first strategy. So coming up with a better weighting term for the gradients. And the first is called discounting. So when you think about it, in a lot of these different environments, there's a delay between taking an action and actually receiving a reward. So let's say I'm playing that Pong game. Then in some sense, like the very first action that you take in the game uh, really has a very, very loose connection with the eventual reward, which is like whether you win the game or not. In contrast, like right at the end of the game, maybe the ball is uh, moving and it's clear that you're going to win. And so that has a really clear correlation with the reward. So what you can do is you can take into account this delay and use what's called discounting. And so you introduce this factor, which basically reduces the amount that an action is kind of rewarded based on how far it is from the reward. So let me just show the example because the formula can be kind of tedious to go through. Let's say that we use a discount factor of 0.9 and we receive a reward only at the very end. Then our action at the end would get 1, this would get 0.9, this would get 0.9 squared, and so on. Okay, and then this is the kind of general formula which allows you to get rewards at different places, things like that. So this is a kind of naive, it might seem kind of naive, but when you think about it, it's kind of really general in the sense that you don't really have to have any assumptions about your environment or the problem you're working on. This gives you some way of kind of assigning rewards to these intermediate steps, even if you get a reward right at the end. And then the other thing you can do is called baseline. So here, let me just motivate it kind of intuitively. So let's say that we're training a language model, and we have these two different prompts. So one is summarize this paper, and the other is prove this theorem. Then what the baseline does is it can take into account the kind of expected reward for your current state. So maybe the model is good at summarizing things or natural language tasks. So just a priori, we expect it to get a kind of relatively high reward. And we can adjust our rewards kind of with respect to the baseline. Okay, so for instance, let's say we got a 0.8 on this like summary that was generated. Then relative to what was expected, it's slightly higher. But if we got a 0.3, then that's actually a pretty bad summary relative to what was expected. In contrast, if the model's like not very good at proving theorems, then maybe you don't expect to get that much reward. So in that case, getting a 0.3, we might actually want to like increase, kind of upweight that or give it a positive reward. So that's the kind of intuition behind the baseline. And what you do is you basically do what I was saying before. Here you could see where the baseline is included. You are basically subtracting it from the return, and that is coming up with a new weight for the gradient. Now you can kind of formalize what I was saying before. This idea of like better than expected, or what is the expected reward? Well, you can literally define like the expected reward and try to use that as a baseline. So does anyone remember this formula and maybe where we saw it come up earlier? Like what is this function called? Yeah, the value function. So a really common choice is you can try to train a value function which predicts at each state what is the expected return or expected reward. And then you can use the value function as a kind of baseline, and that'll help stabilize the policy gradient. So actually there's a code example of this as well. And this has this nice intuition, which is you are going to increase the log probability based on how much better than expected this action is. And then technically you can actually show that these baselines can reduce the variance, like the statistical variance in this gradient estimator. So they're kind of very justified things to do and very common if you're using policy gradient. Then you could say like, well, why do we have to follow this format here? In general, like what is just the best possible weight for the policy gradient? So nowadays, especially, this is referred to as advantages. There's like a technical definition of advantage, um, but a lot of times people just refer to this weight as an advantage. And then you could think of a variety of methods for computing this. So you could think of the baseline as being one way of computing the advantage for this time step. There's other ways based on what's called TD, temporal differences. So here you could see that there's a value function involved, and it's basically looking at like the difference between the value function's prediction for like the current state and the next state. I'm just going through this, you know, a bit quick as a bit of a survey. And then these TD methods have been incorporated into kind of more recent or more complex methods. So this is one, and you'll still see it pop up nowadays, um, called generalized advantage estimation. And this is basically this really general formula. And based on setting these hyperparameters, you can either get baselines or this like temporal difference as a special case. And then you can also do some kind of like interpolation of them in between. But anyways, there's been research like specifically going into estimating good advantages. And so in the next lecture, we'll actually look at ones that people use with language models. So one of them is based on like generating multiple outputs from the model and kind of using the mean and the standard deviation. Um, yeah, remember this idea of advantages because we'll see it in the next lecture. Okay, and then the kind of last improvement is large updates. So you could imagine that these gradients of these updates that you're doing are pretty noisy. And so if you kind of commit too much to a particular update, then it can kind of derail the training. And maybe that's why there's some of these crashes. So at a high level, one mitigation is to try to not move the policy too much at once. And it turns out you can do a bit better than just like reducing the learning rate, because that would, cause things to not move too much at once. But then that would really slow down the training. Um, it turns out that you could use this kind of ratio, and what it's saying is it's saying you have some old policy. So let's say this is your model. Uh, you like, yeah, take a copy of your model. Then you do a few updates and you say, okay, how much does my new model's prediction differ from the old model? Okay, and so if the prediction differs a lot, then that means that the policy has moved a lot. And if the prediction is roughly the same, then that means it hasn't moved that much. Okay, so it's a kind of way of formalizing what I was saying. And then given this ratio, you can kind of incorporate it into a loss function. So this is a really popular loss function or training method called PPO, or proximal policy optimization. And this has been used in a lot of the works on language models and reinforcement learning. So we'll see this again on Thursday. And it's basically this combination of this ratio, and then this A is the advantages, and then you basically do some clipping. So the clipping here is saying um, if you kind of move too far, if the ratio is too large, then you'll just truncate it at a given point in either the positive or the negative direction. Here it's using X and Y. So this is kind of showing a language model. So maybe it's a preview for next lecture, but you could basically apply this to the general, states and actions as well. Okay, so now if we put this all together into an algorithm, there's been a lot of formulas and things like that, but really the core is just a few different changes. So again, we collect these trajectories with the policy and by interacting with the environment. Now, instead of computing just the returns, we compute these advantages. And the advantages might involve, based on the strategy we use, it may involve some baseline, it may involve some value function, it may involve discounting. But you can imagine just like some function called compute advantages, and then you can, pick your strategy. Now, instead of just the policy gradient loss, there's these different options that have, been developed. So for instance, here we could use this PPO loss that I showed on the previous slide. That one in particular requires this like old copy of the model. So yeah, you have to think about what's needed to compute the loss. And then again, you update the policy. Um, so, so yeah, just as one example of this. So in the next lecture, we'll actually see this PPO loss. I made an implementation of it for the next class to like train a language model with it. But for this one, I made this really simple value function baseline. So here again, the value function just takes in the state and tries to predict the future reward. And so now when we're collecting these trajectories, you can just get the value of the current state. And then here you could see, I guess let's just say compute advantages. Here you could see we're basically subtracting the value from the returns. So that's basically the formula that I showed you before in the slides. Then you could say like, how do you train the value function? Well, here it's pretty simple. So you have the true returns that you observed, and then you have the predicted values, and you could use this like mean squared error between the two things. So yeah, you would really want to do maybe some like systematic experiments to investigate this, but here when I kind of implemented the simple value function, the training did turn out to be a bit faster and a bit more stable. But in general, yeah, these kind of techniques really do help. And, it's one reason why a lot of the current methods will not just be using the very, very basic policy gradient. There's also this visualization showing like which states, or basically like what is it assigning high and low values to? So for instance, uh, let's take a look here. It looks like, if the cart is roughly in the middle of the screen, then that's probably a good thing, and it kind of learns that. Whereas if it's way off to the side, then maybe it's already kind of going crazy. So that seems to be learned. Okay, any questions? I guess I haven't paused for questions in a bit. Any questions?
I think I was wondering, are there a lot of modern methods that share weights between the policy and value?
Yeah. So one common thing to do is you just attach an extra output head to compute the value function.
Is that is it called full fine tuning, or is that just that head that gets trained with?
Yeah, as far as I know, it kind of depends. You try each different thing. So one thing is to just train, yeah, like you'd want more than one layer so that it's nonlinear, but you could try to just train that part, or you could back propagate through. Yeah. And then sometimes it's better, for a really complicated value function, it might be even better to like pre-train the value function or have separate parameters for it. In this cart pole example, there's like many different algorithms work for cart pole, so probably any of the combinations work for cart pole. Yeah, it turns out even like these evolutionary style algorithms that like take the gradients and then use random noise, uh, even that can solve cart pole. But anyways, okay. Any other questions? Mhm.
So it seems that the tweaks that we're doing are just to like slow down updates when we're close to like a good solution. But for example, in like a three pendulum problem, uh, there are like two stable states that's like upside down or like the other way around.
Mhm.
So in that case, there are like good states and bad states,
Mhm.
but that's not reflected in what we are doing here, right?
Yeah, maybe what you're getting at is that we're not really saying how to explore or how to find good states or bad states.
Yes.
Is that, yeah. Yeah, so here the exploration is just based on sampling from the policy. And so for really uh long horizon tasks, so let's say you're playing the Atari game and you don't get a reward until like 10,000 steps. Um, then you're gonna need some strategy for doing better exploration. Um, so in those cases, just what I'm showing before actually, yeah, probably won't be enough because you'll just never stumble upon these kind of good states. Yeah. Yeah, actually with the Atari games, there was like one of them's called Montezuma's Revenge. So back in the day when people were trying to solve these, it was like all the scores were high except for Montezuma's Revenge and some other environment, because again, they're like really, really long horizon. So the model would just never get kind of positive rewards. Okay, and then just as a preview, so again, we're going to apply this to the language models in the next lecture. Um, and it'll kind of be these special cases if you want. But then, you could imagine to get it to work in practice, there's still a lot of innovations and important details. So we're going to take a look at the setting called reinforcement learning from human feedback. Here, we will want to basically train a model so that it optimizes human preferences. So it like generates responses that humans prefer. So we'll talk about how to, one way of um, kind of quantifying human preferences and then optimizing it with reinforcement learning. And then we'll also talk about this kind of recent setting, which is maybe arguably even simpler, but it's more, recent uh, that it's kind of taken off. And it's called RL with verifiable rewards. So here you can imagine like human preferences is kind of hard to evaluate, but there's things that are really easy to evaluate, like whether the answer to something is correct or not, um, uh, like in these math problems. And so you can use that as a kind of reward and then do reinforcement learning. So you may or may not have heard of this DeepSeek R1. It kind of made big news and everything. And this kind of led to a whole new kind of area of research that people have been looking into recently. So we'll take a look at this in the next lecture.